In this lecture, I'm going to introduce formal power series. Let F be any field. For some of the calculations that I'll do later, F will need to be a field of characteristic 0. But for the definition of formal power series, you can take F to be any field or even a commutative unital ring. Then a formal power series in F is just an expression It's an expression of the form f of x equals summation n equal to 0 to infinity an x to the n, where these coefficients a0, a1, a2, these are all elements of the field f. You should not think of this f as a function, because if we take a field like a finite field or just the rational numbers, it's not clear what topology we will be using on this field, and therefore what the notion of convergence of this series is. In fact, we do not want to check any convergence. When you study complex analysis, you look for power series with a positive radius of convergence. Here we do not ask for any such condition. We just think of them as expressions which you can write down like this. So in effect, a formal power series is nothing but an infinite sequence of coefficients in F. And what you can do with these though is the various algebraic operations that you can do with functions. So we have sum of formal power series f plus g of x. So let's suppose that f is summation an x to the n. N goes from 0 to infinity. Gx is summation n goes from 0 to infinity bn x to the n. Then f plus g to the x is by definition the formal power series given by n goes from 0 to infinity an plus bn x to the n. Just the addition of the corresponding coefficients. And multiplication is defined much the same as the way we define multiplication of polynomials. So this is sum n goes from 0 to infinity. K plus L is equal to n ak bl x to the n. So with these notions of addition and multiplication, we denote by f, and then we have these double square brackets fx, the ring of formal power series. So it has a notion of addition, a notion of multiplication, and these will satisfy the axioms for a ring. I should point out that in this ring, 0 is just an equals 0 for all n, and the multiplicative unit 1 corresponds to a0 equals 0 and an equals 0 for all n greater than 0. Let me give you an example of a calculation, a simple but not completely trivial calculation in this ring. Let's say here any field will work. In fx, we have 1 minus x into summation x to the n. So here I'm talking about the power series where the coefficient of all the coefficients are equal to 1. This is equal to, so let's see what this works out to be. So this is the power series where a0 is 1, a1 is 0, a1 is minus 1, and a2, a3, a4 and so on are all 0. So when you write down this product using this formula here for the product, what you see is that this is just summation n goes from 0 to infinity. Let's call this thing summation an x to the n. Let's call this thing summation bn x to the n. then what we are looking at is k plus l equals n, akbl, right? Now a0 is plus 1, b's are all 1, so those don't matter, and a1 is minus 1. So firstly we have this term which just corresponds to n equals 0 where there's no b, and then we have this sum 1 minus 1 x to the n, and so all these higher coefficients vanish, and what we get is that 1 minus x into summation x to the n is actually equal to 1. So we write 1 over 1 minus x is summation n equals 0 to infinity x raised to n, or 1 plus x squared, and so on. And this is the familiar formula for an infinite geometric series, which is usually valid only if x is a complex number with absolute value less than 1. But in this case, it's a formal identity in the ring of formal power series, and this x is just a symbol. Even though the power series are formal, we need to talk about infinite sums of formal power series, and then we will need a notion of convergence. So what I'll do now is I will define a metric space structure, a distance function on formal power series. So firstly, if f is not equal to 0, so let's generally write f of x equal to summation n goes from 0 to infinity a n x to the n, an arbitrary element of the ring of formal power series. Now if f is not equal to 0, which means that at least one coefficient of f, one of these ans, is non-zero, then you define the valuation of f to be the least integer such that an is not equal to 0. And then you define the norm of f to be 2 to the power minus valuation of f. You have taken 2, but you can take any real number strictly greater than 1, and it will give you an equivalent metric, in the sense the notions of convergence will be the same. But for simplicity, we'll just take 2. If you want, you can take e. That's another common choice. And now we are ready to define the distance. Here this is only defined if f is not equal to 0. Define the norm of 0 to be 0. And now we finally define the distance f to g to be the norm of f minus g for all fg in f of x. And this is the distance function and supposed to give the ring of formal power series the structure of a metric space. What are the things we need to check to make sure that this is a metric space? Recall the axioms for a metric space. So the first is that the distance function is symmetric. The distance from f to g is the same as the distance from g to f. And this is not difficult to prove. The thing to note is that the valuation of minus f is the same as the valuation of f. So the norm of f minus g is the same as the norm of g minus f. So this one's pretty easy. Then the second axiom is that dfg is greater than or equal to 0 for all fg in fx, and equality holds if and only if f is equal to g. So dfg equals 0 if and only if f is equal to g. Now this is also quite easy to see, because the distance is, well, the way I've defined the norm, it's always something positive except when f is 0, in which case it's 0. So this distance is always greater than or equal to 0. And if dfg is equal to 0, that means that the norm of f minus g is equal to 0. But if you look at any non-zero element, then it has a valuation which is a non-negative integer, and 2 raised to the negative of any non-negative integer, i.e. 2 raised to any non-positive integer, is certainly going to be a positive real number. And so if f and g are not equal, then f minus g is not 0, and so d of f comma g is going to be strictly positive. The last and most interesting property is the triangle inequality, which says that if you have 3 points in your metric space f, g and h, then if you go from f to h directly, that distance cannot be more than if you go from f to h via g. So it says that for all fgh, d of fh is less than or equal to d of fg plus d of gh. And this is called the triangle inequality. Now let's see what this triangle inequality means in terms of the norm. So here this left hand side is norm of f minus h is less than or equal to norm of f minus g plus norm of g minus h. Now note that if I take f minus g plus g minus h, then they add up to f minus h. And this is equivalent to norm of f is less than or equal to, let's write it like norm of f plus g is less than or equal to norm of f plus norm of g for all fg in ft. So you can rewrite this in this form. And so this is what we need to prove. We need to show that 2 to the power minus valuation of f plus g is less than or equal to 2 to the power minus valuation f plus 2 to the power minus valuation g. In fact, something much stronger holds. What holds is that if you take the valuation of f plus g, so we're looking for the first non-zero coefficient of f plus g. So if f has first k coefficients 0 and g also has first k coefficient 0, then f plus g will obviously have first k coefficient 0. So what we're saying is that the valuation of f plus g is going to be at least the minimum of the valuation of f and the valuation of g. Okay, it could be that it's actually strictly greater For example, if f and g have the same valuation, but then their leading terms cancel out. And this implies that 2 raised to minus valuation f plus g is less than or equal to the maximum of 2 raised to minus valuation f 2 raised to minus valuation g, i.e. the norm of f plus g is less than or equal to maximum of the norm of f and the norm of g. In other words, the distance from f to h is less than or equal to the maximum of the distance from f to g and the distance from g to h for all f, g, h in ft. This of course is less than or equal to the distance fg plus the distance gh. So this implies the triangle inequality, but it's actually a stronger inequality, and this inequality is called the ultrametric property. We'll see in a moment that this has some nice consequences. This is the ultrametric norm property, and this is the ultrametric distance property. We'll see that this has some very interesting consequences, making certain kinds of convergence checking very simple. But let's start with some simple examples of convergence in this metric space. So the simplest example and probably the most important example is that a limit as n tends to infinity x to the n is 0 in ft. Why is that? Well, this is just because distance from x to the n to 0 is just the norm of x to the n, which is 2 raised to minus n, and that goes to 0 as n goes to infinity. Okay, now the first theorem is that every Cauchy sequence in ft converges, i.e. fx is a complete metric space. Every Cauchy sequence converges. So let's prove this. So suppose we have a sequence is a Cauchy sequence in fx. I want to show that it converges. I want to construct a limit for this sequence. So firstly, I claim that let's first just set up some notation. Suppose fn x is summation a n m x to the power m. M goes from 0 to infinity. Okay, so these are the coefficients of fn, and I claim that for every m greater than or equal to 0, what I want to say is that you fix any m and you look at the mth coefficient of the sequence fn. So you look at the mth coefficient of f1, you look at the mth coefficient of f2, and so on. This will stabilize. So after some point there exists n, a positive integer, such that for all n1, n2 greater than n, a n1 m is equal to a n2 m. And the proof of this claim is very simple. Just take epsilon to be 1 over 2 to the power m, and now use the condition for being a Cauchy sequence. So Cauchiness implies, Cauchiness, is that a word? Implies that there exists n in P such that if n1 and n2 are greater than n, then n1m equals, no, that's not what it implies. It implies that fn1 minus fn2 is less than epsilon, which is 1 over 2 to the power n, which means that the mth coefficient of fn1 minus fn2 is 0. So this means that amn1 minus amn2 is 0, because only some coefficient after that vanishes for this norm to be less than 1 over 2 to the m. But that's exactly what we wanted to show. Okay, so that proves this, and it says, so what we're saying is that for every m greater than or equal to 0, the sequence ANM is eventually constant. So what we'll do is we'll define the limit to just be the series whose coefficients are those eventually constant values. Say, taking eventually constant value A, let's just call it AM. Then you let f of x be the summation n goes from 0 to infinity an x to the n, and we'll have, it is easy to see that limit n tends to infinity fn of x, well, let's just write it like this, fn is equal to f. I'll leave that as an exercise for you to check. Now we come to a magical property of this space of formal power series. When I used to teach calculus, students used to often make this mistake, but here it's actually okay. And here's the theorem that suppose limit as n tends to infinity, fn is equal to 0, then the infinite series n equals 0. So now I'm going to look at a series of formal power series. Maybe, I don't know. Yeah. Fn converges. What do we mean by a series converges? We just mean that its sequence of partial sums converges. And this, of course, is not expected in the real numbers. For example, if you take the harmonic series 1 over n, 1 over n goes to 0 as n goes to infinity, but the harmonic series summation 1 over n does not converge. However, in this case, it does converge, and it is because of the ultrametric property. So here's the proof. So I need to show that the difference between two partial sums will become small. So given any epsilon greater than 0, find n in P such that for all n greater than n, fn is less than epsilon. So here I've just used the hypothesis that limit n tends to infinity, fn is equal to 0. Then for all n1 greater than n2 greater than n, if we look at the difference between the partial sums, so n equals 0 to n1, fn Well, okay, we are starting the summation at 1 minus n equals 1 to n2 fn. Well, this is going to be, so this is the distance between these two things. This is going to be just the norm of the sum n goes from n2 plus 1 to n1 fn. But by the ultrametric property of the norm, this is less than or equal to max of f n2 plus 1 up to f n1. The norm of a sum is less or equal to the maximum of the norms. This is just a finite sum. And so this implies that n equals 1 to capital N fn, this sequence of partial sums is a Cauchy sequence. And hence it converges. Maybe I should say, I don't know, something. This is a Cauchy sequence and hence it converges, and so this infinite series converges. So let's see some nice applications of this example. So suppose we have a formal power series with summation n goes from 1 to infinity a n x to the n with a0 equal to 0. Now I told you that we shouldn't think of these formal power series as functions, but we tend to use certain analogies with functions. If you had an actual power series which was convergent in some region, then this a0 would be the value of the power series at x equal to 0. So this condition we will often write as f of 0 equal to 0. Okay, so when I say f of 0 equal to 0, you should understand that to mean that a0 is equal to 0. Then I'll just take the sum n greater than or equal to 0 or n equals 0 to infinity f to the power n. This converges. Why is that? Well, if f0 equals 0 implies that f of x is equal to x times g of x for some function gx. Well, some formal power series gx, not functions, right? So, but then that means that f of x to the power n is equal to x to the n times gx to the power n, which implies that the valuation of f of x to the power n is greater than or equal to n, because all the terms will have coefficient at least, all the non-zero terms will have coefficient at least x to the n, will have power of x at least x to the n, which implies that the norm of f of x raised to n is less than or equal to 1 over 2 raised to n. So this sequence converges to 0, and therefore by the preceding theorem this series converges. So convergence, deciding convergence in formal power series is usually not at all a difficult thing. Okay, and we'll use this to give a nice simple theorem for what are the units in the ring of formal power series. So the theorem says that f of x equals summation n equals 0 to infinity a n x to the n has a multiplicative inverse in f of x if and only if a0 is not equal to 0. And I'll in fact show you how to compute the multiplicative inverse. So firstly, let's prove that if f has a multiplicative inverse, This is the easy part. Call it G. Then what's easy to see is that 1 is equal to fg, but if I evaluate it at 0, that should still hold, by which I mean take the constant term. But this is equal to f0 g0. So this means that if f0 into something is 1, then this means that f0 is not equal to 0. Okay, so that way is easy. And the other way, conversely, suppose a0 is not equal to 0. Then I can write f of x as a0 times 1 minus h of x minus h of x, where h of 0 is equal to 0. Right? I just isolate the a0 part, and h of x is going to be minus a1 by a0, x minus a2 by a0, x squared minus. This makes perfect sense because a0 is non-zero. And so by the previous result, we have that sum n goes from 0 to infinity, f of n converges. And moreover, 1 minus f, not fn, hn converges. And moreover, 1 minus h inverse is this, or maybe I'll write it like this: 1 minus h times sum n equals 0 to infinity, hn is equal to 1. I'll let you think about why this is true. Therefore, what we get is 1 minus h inverse is equal to summation n goes from 0 to infinity hn, and so we can compute the inverse of f of x. Therefore, f of x inverse is equal to a0 inverse times summation n goes from 0 to infinity h of x to the power n. A very explicit value for the inverse of f of x. Now, one way in which formal power series are used are as generating series for interesting sequences of integers. As Herbert Wilf says in his book Generating Functionology, a generating function is a clothesline on which we hang out a sequence for display. So let's just take an example of how we can hang out a sequence, and once it's hung out, we can get a very clear picture of what it is. What better place to start with than the Catalan numbers? N goes from 0 to infinity are defined by, well, one way is that they are the number of non-crossing partitions of 1 to n, but we'll just take the more pedestrian approach and say C0 is equal to 1 and Cn is equal to sum over k plus l equals n minus 1 ck cl. Now let's hang this out for display. So if we write f of x to be the sum n goes from 0 to infinity Cn x to the n. Notice that these Catalan numbers do seem to grow, so it's by no means clear when this series converges and so on, but in a sense we don't care because we are working with formal power series. And once you write this down, you can reinterpret these identities. These are saying in terms of generating functions that f of x is equal to 1 plus x times f of x squared. because if you look at the coefficient of x to the power n on the left hand side, for n greater than 1, it's going to just be Cn, and on the right hand side it's going to be precisely this sum, k plus l equals n minus 1 ckcl. This n minus 1 is coming because there's an x outside, and so that will take the coefficient up to x. It will take the power of x 1 higher than what you would have in f of x squared. And so instead of k plus l equals n, we have k plus l equals n minus 1. So we have this very simple identity involving the generating function of the Catalan numbers. In fact, this is just a quadratic equation. I can write it as x f of x squared minus f of x plus 1 equals 0. This is a quadratic equation in the variable f of x, and its coefficients are in if you wish, you could say the coefficients are in polynomials in f, and so we can solve it using the quadratic formula. And what you get is that f of x is equal to, so the usual quadratic formula, if you have an equation ax squared plus bx plus c, then the solutions are given by minus b plus or minus square root of b squared minus 4ac by 2a. So when we apply it here, we get minus b, so that's just 1, plus or minus b squared, which is 1, and I'll write minus 4ac, so which is 1 minus 4x, and I'll write square root as to the power half divided by 2x. Now if you look at the coefficient of x to the power 0, that is the constant term up here, since there's a 2x in the denominator, this will not be divisible by 2x unless that constant term is 0. So we better take the negative sign here, otherwise this will not make sense. So if there is a solution, it must be the negative sign. Okay, so it cannot take the positive sign. And now we'll use the binomial expansion for 1 minus 4x to the power half. And you need to check this, but it turns out in the ring of formal power series, a square root of 1 plus y is given by this formula. It's just like the usual binomial formula, n choose k. Well, here it's half choose n, y to the n. Whereby half choose n, what I mean is summation. So if I say alpha choose n, what I mean is alpha into alpha minus 1 dot 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 alpha minus n plus 1 divided by n factorial. So for this, you don't need alpha to be an integer. Alpha can be even a formal symbol, and so certainly half choose n makes sense. And if you work out what this means, you will see that this is minus 1 to the power n plus 1 divided by 4 to the power n to n minus 1, and then we get 2n choose n y to the power n. Okay, so you just need to work it out. You'll get half into half minus 1 into half minus 2 and so on, and those will end up being products of odd numbers divided by some power of 2 and so on. So that's what you get over there. And so 1 minus 4x, substituting 4x for y here, is equal to summation n greater than or equal to 0 minus 1 over 2n minus 1, 2n choose n, x to the n. Therefore what we get is f of x is equal to summation n greater than or equal to 0, 1 over n plus 1, 2n choose n, x to the n, which implies that the nth Catalan number is 1 over n plus 1, 2n choose n. So here's an example of how you could use formal power series to actually derive a formula for the nth term of a series. using some sort of recurrence relation that define the sequence that you are interested in. I would encourage you to fill in all the steps in this calculation here and make sure that this is exactly what we get. Now, even though formal power series are not functions, we can do many things that we can do with functions with them. And one is composition of formal power series. We need to be slightly careful here. And this only works if g of 0 is equal to 0, i.e. the constant term is equal to 0, and f of x is equal to summation a n x to the n. Then we define f circle g of x to be summation n greater than n equals 0 to infinity. And what you're doing is you're just substituting for the variable of x the function gx. So you'll write this as a n gx to the power n. And this makes perfect sense, because if g of 0 is 0, then this sequence gx to the power n goes to 0, and therefore also the sequence a n gx to the power n goes to 0, because the valuation of this will be the same as the valuation of gx to the power n if a n is non-zero, and of course its norm is going to be 0 otherwise. So this sequence also goes to 0, and so this makes perfect sense. This thing converges. So for example, x of xx minus 1 makes sense, where I need to define what this exponential function is. Now the moment I write this down, you need to be careful. This will not work if f is a field of a finite characteristic, of positive characteristic. This will only work in a field of characteristic 0. So this very important transcendental function is not available to us in a field of positive characteristic. So now when I'm doing these calculations, it's better to assume that f is a field of characteristic 0. Just take it to be the rational numbers. So this makes sense, but this does not. If you try to write this sum with g of 0 not equal to 0, then this series will not converge, and so we do not have a formal power series that corresponds to this infinite sum. It turns out that this is the exponential generating function for the Bell numbers. We'll see this later. Exp of x minus 1 is summation n goes from 0 to infinity bn by n factorial x to the power n, where bn is the cardinality of the set of set partitions of 1 to n. These are called Bell numbers. Now let's look at another example. Suppose f is a function then define L of x, which I will be calling log of 1 over 1 minus x. This will become clear why I mean that in a bit, as summation n greater than or equal to 1 xn over n. So of course, from your study of analytic functions over real numbers and so on, you would know that L of x is the log of 1 over 1 minus x has this power series expansion about 0. Okay, if you want n equals 1 to infinity or n greater than or equal to 1, it's the same thing. So let me justify this notation why it's called log of 1 over 1 minus x. So this is a function of the kind we like. L of 0 is equal to 0. Its coefficient constant term is 0. So it makes sense to talk about composing it with exp. So exp of L of x, well, this is summation n goes from 0 to infinity L of x raised to n over n factorial. Now if you try to compute this, this ends up being n goes from 0 to infinity 1 over n factorial, and then if you look at this L of x raised to m, so I'll just write it out. M goes from 1 to infinity x to the m by m to the power n. And if you think about what this should be, this is a sum over all m1, m2, mn, all possible n's. The coefficient of x to the power n is going to be, so maybe I should write it like this, sum over just write 1 over n factorial 1 over m1 m2 mn. Now you can try to compute these sums for the first few values of capital N, and this should be if there is any justice in my notation, this should be 1 plus x squared, which means that this inner sum here should be equal to 1 for every capital N. Okay, so I'd encourage you to play around with this and try to see that this is indeed the case. But to actually write down a proof, we will use a new idea and we'll get a very simple proof. We'll use the notion of differentiation. Again, these are not functions, but we will pretend they are functions and do the various operations that we do on functions. So let me introduce a new operation on formal power series, namely differentiation. Suppose fx is equal to summation n goes from 0 to infinity a n x to the n. Then I define f prime x, alternatively sometimes this is also called d dx f of x. This is defined to be the power series, formal power series n greater than or equal to 0, n plus 1 a n plus 1 x to the power n. So a n x to the power n minus 1 is the derivative of a n x to the power n, but I need my numbering to go from 0 to infinity, so I'm just going to change this to n plus 1 a n plus 1 x to the power n. So that's the formal derivative of the formal power series. Again, we don't need to assume that this is a function or check any limits or anything. That's just it. But it still satisfies all the nice properties of the usual derivative. We have firstly f plus g. The derivative of f plus g is the derivative of f plus the derivative of g. And we have the product rule. F g prime is f prime g plus f g prime. This implies, so these are easy to check at the level of coefficients. I would encourage you to check these by hand. This second rule implies, by applying it repeatedly, that if I take d dx of gx to the power n, then this is n times g prime x gx to the power n minus 1. This is a special case of the chain rule for derivatives. It just comes by using this product rule inductively. And using this 3, you can get the chain rule for formal power series if g of 0 equals 0, then d dx of f, well, maybe I'll write it as f circle g prime is equal to g prime, well, let's write it like this, f circle g prime x is equal to g prime x times f prime circle g of x. The usual chain rule that we have for derivatives, and it just follows by applying 3 to the definition of f circle g and differentiating. So now let's go back to our logs. So what we have is Lx, remember we defined this to be log of, well, no, we defined it to be summation n goes from 1 to infinity x to the n by n, formal power series. And so what we get is d dx of Lx is just, if we differentiate this, we'll just get 1 over 1 minus x, because derivative of x to the power n divided by n is just x to the power n minus 1. So all the coefficients of the derivative are going to be 1. And on the other hand, d dx of x is exp of x. This again you can check by just using the formal definition of exp of x, x to the n by n factorial, and using the formal definition of the derivative. So these are easy to check, and we have the chain rule and so on. So let's define u of x to be exp circle L of x, and let's differentiate. D dx of u of x is equal to L prime x exp circle L of x, but that is 1 over 1 minus x ux. So this is a differential equation satisfied by the formal power series ux. So we have ux is equal to 1 minus x u prime x. Now you just write down the power series expansion. Suppose ux is equal to summation n goes from 0 to infinity a n x to the n. Then what we have is that summation a n x to the n, that's the left hand side of this identity, is 1 minus x summation n goes from 0 to infinity n plus 1 a n plus 1 x to the power n, which is equal to n plus 1 a n plus 1 minus n a n x to the power n, except of course when n is equal to 0, where we get 1. Because the constant term of the right hand side here is 1. Actually, it's not clear why that's 1. Let's just write it like this. Okay, so this is this, and when we take n equals 0, then we just have a0. Okay. Now if you solve this, then what you get is that if you equate the coefficients on both sides, what you get is that an is equal to n plus 1 an plus 1 minus nan, which is the same as saying that n plus 1 an plus 1 minus an is equal to 0, which implies that an plus 1 is equal to an for all n greater than or equal to 0. Yeah, I think here I can write this. Yeah. So, so this means that all the coefficients of ux are equal to are the same. Therefore, ux is equal to a0 divided by 1 minus x. But you can compute the constant term of u of x. U of 0 is equal to, well, exponentiation of anything, the constant term will be 0 because the first term will be 1. So equals 1 over 1 minus x. So what we have is x of L of x is equal to 1 over 1 minus x. So with this justifies log of 1 over L of x is log of 1 over 1 minus x. We can call it log of 1 over 1 minus x, and it's given by the formula n goes from 1 to infinity xn by n. So this became much simpler using the notion of differentiation. Let's play a little more with logs and exponentials. Here's a easy lemma that if you take x of, so now we need to assume that f of 0 is equal to 0, and so is g of 0 is equal to 0 for two functions f and g in formal power series in a field f of characteristic 0. So x of fx plus gx makes sense. Well, this is equal to x of fx plus times x of gx. Let's prove this. We'll start with the left hand side. X of fx plus gx by definition is equal to the sum n goes from 0 to infinity, and then we would take f of x plus g of x raised to the power n divided by n factorial. But that's equal to summation n goes from 0 to infinity summation, and now we will take k plus l equals n. We'll employ the binomial theorem, and we have n choose k fx to the power k gx to the power n, and then we still have divided by n factorial. But if you work that out, that is summation n goes from 0 to infinity summation k plus l equals n, and this n choose k is n factorial divided by k factorial l factorial. This n factorial will cancel out with this n factorial over here, and what we'll get is fx to the power k by k factorial gx to the power l divided by l factorial. But this is nothing but the definition of x of fx, the product of the series x fx and x gx. So the exponential has this, well, what we call the exponential property. Okay, now I want to define the log of a more general class of functions. So note that if you take any function such that f of 0 equals 0, then its exponential will always have constant term equal to 1. And so if we want to take the log, we should expect that the function that we are taking should have constant term equal to 1. So suppose f of x in formal power series is such that f of 0 is equal to 1. Then what I can do is I can write take gx equal to just 1 over 1 minus 1 over fx. Now note that fx has constant term equal to 1. So 1 over fx also has constant term equal to 1. And so this g0 is 0. And so it makes sense to define. So this identity though is equivalent to saying that f of x equals 1 over 1 minus gx. So these two are equivalent, and we have g of 0 equals 0 when I write f of x in this form. So define log of f of x to be, well, inspired by our earlier thing. It is just L composed with g of x, which by definition is summation n goes from 1 to infinity gx to the power n by n. This makes perfect sense. This is a convergent sum. So using this, we've been able to define the log of any function whose constant term is equal to 1. Moreover, you can show that x of log of fx is equal to fx for all f in fx with f of 0 equal to 1. Okay, now I want to show that the log has the property of turning products into sums. So if f0 equals 1, g0 equals 1, then log of fg is equal to log of f plus log of g. To prove this, what I'll show is that x of f log of f of g, that is the exponential of the left hand side, well, this is certainly equal to f times g. What about exponential of the right hand side? Well, using the exponential property of the exponential function, this is x log f, x log g, which is again f times g. So the exponential of the left hand side is equal to the exponential of the right hand side. And so to conclude that the left hand side and the right hand side are equal, I need the following lemma. If exp of f of x is equal to exp of g of x for any functions f and g with constant term 0, then f of x is equal to g of x. To prove this, you first show that exp f of x equals 1 implies that f of x is equal to 0. Okay, this is not very difficult. And then the second step you show is that therefore if exp f of x equals exp g of x, then what you get is exp f of x minus g of x is equal to 1. And from this implies that f of x equals exp g of x implies that f of x equals g of x. So we just use the property of the exponential to prove the corresponding property of the log. Now the last thing I'll do with these logs and exponentials is to treat infinite products, which are quite useful in combinatorics. So suppose we have a sequence of functions. Let's say n goes from 1 to infinity, such that, so a sequence in formal power series such that limit as n tends to infinity, fn is equal to 0. Then I will define product n greater than or equal to 1 over 1 minus fn as exp of summation n equals 1 to infinity log of 1 over 1 minus fn. This infinite sum of course makes sense, because you can show that if limit as n tends to infinity fn goes to 0, then so does this limit as n tends to infinity of log of 1 over 1 minus fn goes to 0, because after all log of 1 over 1 minus fn is summation fn raised to m by m goes from 1 to infinity, and so the valuation of log of 1 over 1 minus fn is equal to the valuation of fn. So this makes perfect sense. This is well defined. Also, each of these summands has constant term 0, so the total sum has constant term 0. So as an example, we define Px to be product n greater than or equal to 1 over 1 minus x to the power n. So this you can think of as 1 plus x squared, 1 plus x squared plus x to the power 4, 1 plus x cubed plus x to the power 6, and so on. Or if you wish, you can write this as product sum over, but let's write like this first: product I goes from 1 to infinity sum mi goes from 0 to infinity x to the power I mi. But using distributivity, you can show that this is the same as summation m1 greater than or equal to 0, m2 greater than or equal to 0, and so on. Product I goes from 1 to infinity x to the power I mi. So the coefficient of x to the power n is the number of indices m1, m2, and so on, such that summation I times mi is equal to n. That's the coefficient of x to the power n. That's how many times you'll see x to the power n over here. But this turns out to be the number of integer partitions of n. In fact, if lambda is equal to lambda 1, lambda 2, lambda L is an integer partition, then you let mi be the number of times lambda j is equal to I. So we will write this as 1 to the power m1, 2 to the power m2, and so on. This is called the exponential notation of the integer partition lambda. So if you know the multiplicity of each integer in the integer partition, then you know the integer partition. For example, if we have the integer partition 3, 2, 2, 1, 1, 1, then this is the same as 1 occurs 3 times, 2 occurs twice, and 3 occurs once. So m1 is equal to 3, m2 is equal to 2, m3 is equal to 1. And the size of this integer partition is 3 into 1 plus 2 into 2 plus 1 into 3, summation I times mi, and that's equal to 3 plus 4 plus 3, which is 10. And so what we get is the famous factorization due to Euler. We'll visit this again, but this is just a quick Pn x to the n is equal to product n equals 1 to infinity 1 over 1 minus x to the power n, where Pn is the number of partitions of n. We will revisit this later with much more care.